All right, in this video, we're going to take a look at how to write electron configurations for large electron elements in a short way, a shortcut. That's what we're going to call it. This is the electron configuration shortcut. And so I want you to think about, let's take a look here at, say, for example, we'll go over here. So selenium and bromine, right? Let's start up here. Let's do oxygen and fluorine, right? So if I'm writing out the electron configuration for oxygen, I see that it is, first of all, it's 1s1, 1s2. So oxygen would have an electron configuration of 1s2, 2s2, and then we see it's 2p, 1, 2, 3, 4, so 2p4, right? And then if we did fluorine would be 1s2, 2s2, 2p5. If we were to write neon out, it would be 1s2, 2s2, 2p6. And then finally, if we were to look at sodium, it would be sodium Na would be 1s2, 2s2, 2p6, 3s1. What's interesting, if we look in particular, we see here the pattern is every element, every time you move to the right one element, you just are moving up one electron, and so you adjust the electron configuration accordingly. However, when you go from one row to the next, so we were at neon, we were in period 2 or row 2, and we go down to sodium, which is in now period 3, what we see is something interesting. The electron configuration of sodium is exactly the same as neon, except for this 3s1. In fact, if we look here, 1s2, 2s2, 2p6 is the same as the sodium. And so a shortcut for writing large electron configurations is called using the noble gas, the kernel, and that is spelled this way, so the kernel. And we can abbreviate, we can take this 1s2, 2s2, 2p6 here in the sodium and just write it like this, which signifies that the first 18 electrons are just like neon, and then there's the 3s1. And so this would be, this would suffice for an electron configuration for sodium. Okay, so this shortcut's really helpful when we get to some of the larger elements. So let's take a look at a large element. Let's do, pick rhenium here in the middle. So here's rhenium. Okay, so since we decided to do rhenium, to use our shortcut, we first have to figure out what's the noble gas in the row above rhenium. So we go up here and we see the noble gas above rhenium is krypton. That's 36. So that means the first 36 electrons of rhenium are exactly like krypton. So I can write the electron configuration for rhenium, RH there. I can write the kernel, which is krypton. And the kernel means the complete energy levels. So the first 3 energy levels, 1, 2, and 3, first 4 energy levels for rhenium are completely full. And so we say that that's a krypton kernel, or the kernel, that's the inner 4 energy levels. Okay, so then we have krypton, so then we go down here to our period 5, and we see that rhenium is going to be 5s2, and then we're going to move over 1, 2, 3, 4, 5, 6. Oops, sorry. 1, 2, 3, 4, 5, 6, 7. And then it's going to be 4d7. Remember, when we're in the D sublevel, that our energy level is 1 less than the row that we're in. So we're in the 5th row, so this is actually the 4d sublevel. Okay? So that's how it works for rhenium. We can do one more here. Let's look at, say, we'll go to 6. Let's do cesium, right? So very easy here. We can look and say cesium is the first element in row 6. And so the noble gas we're going to use is the one in the row preceding that, which is xenon. So our electron configuration for cesium is simply going to be xenon and then 6s1. Okay? So this shortcut can help you with some of the lengthier electron configurations. Let me know if you have any questions, and copper tomorrow.